Hello friends, welcome to my channel. Today we are doing a part 2 for the shear wall design with boundary elements. We have done in the first part that we have find these effective depth, factor bending moment, factor shear force, section classification we have done, design for shear reinforcement we have done, maximum spacing for the vertical and horizontal bars we have found out, horizontal shear reinforcement we have calculated, and minimum vertical reinforcement for the shear wall we have calculated, shear check we have done. Now in this part 2 boundary element check, we have to first find the boundary element is required or not, and then we have to give the sizes in this, and flexure strength we have to find what is the moment capacity for which the boundary element which is to be designed as a short column. These are the boundary elements and this is the shear wall, right? So design for boundary element as short column, check for tension and confining reinforcement, that is the ties for the boundary element, what is the spacing for that ties, right? So let's start. What we have done, we will do it very quickly. That HW, we have given the HW height of the wall is 9 meter, LW is the shear wall length 4 meter, TW is the thickness of the wall 250 mm, FCK is M25 and FY is 415, right? So effective depth is calculated 3200 by this formula, factor bending moment MU is calculated, and VU factor shear force is calculated 930. Section classification already done. We have already done these things in part 1, explained in detail. This is a slender wall. Design for shear reinforcement, tau V is calculated 1.16, tau C is this by this formula 1.25, tau max by this table for M25 is 3.1. So steel will be provided in 2 curtain layer because we have the width of the wall is 250 mm. If it is 200 mm, then it will be steel in single layer, right? So it is more than 200 mm, so we have to provide the steel in 2 curtain layers. Maximum spacing by these 3 formulas, maximum spacing is the least of the above 3, that is 450 mm, it has been calculated. Horizontal reinforcement we have provided by this formula, this is 0.25% we have to provide, so we have chosen 10, so 251 mm, so we have provided 250 mm. So provide 10 mm bar 250 mm center to center horizontally for horizontal reinforcement. Check for shear reinforcement is okay. Minimum vertical reinforcement, if we are providing 10 mm, so 180 mm center to center is vertically, it has been calculated. So this has been explained in detail in first part. So shear check is okay. Now the boundary element check in this part. So factored axial load is given by this formula 3432, we have already calculated. So stress is given by the stress, because the horizontal force of the earthquake will be applied on this part, so this portion will be in the compression and this portion will be in the tension. So we have to calculate the stress by this formula, right? So F max is 13.175 by this formula, PU upon A plus MU by Z. F minimum is minus 6.8 because this is the tension, so it will be negative. So clause number 10.4.1 is that if F max is greater than 0.2 FCK, this is 5, right? So F maximum is 13.75, so this is boundary element shall be provided, right? So if we change our moment capacity by 800, boundary element is not required, so we do not have to do it for the boundary element check, and the whole shear reinforcement will be provided, right? These reinforcement calculated earlier will be provided in whole wall. In our case the moment is, this is 5120 and this is 2400, so let's check. F max is 13.75 and F, this is calculated as 5, so this is greater than 5, so this is boundary element shall be provided. So we have to choose the size of the boundary element. If we provide the thickness of the this boundary element as equal to the thickness of the wall, then we have to choose 250 mm, and D, this is the depth of the boundary element. If you provide this 500, so you can see that these are the formulas, right? We have to calculate the flexure strength of the wall, how much the moment capacity of this wall be taken by the shear wall, right? So and the additional movement we have to provide the boundary element and we have to provide the reinforcement. Are you getting this point? So PU is calculated by this formula. Vertical reinforcement provided, already calculated, 872. This is vertical reinforcement, 872. Total vertical reinforcement is provided in this is the shear wall, and total vertical reinforcement provided in this length, right? Now this formula is according to the annexure A, case A, rho is AV by TW into LW. We already know all these things. AV is calculated, TW is the thickness of the wall, LW is the length of the wall. So this is constant 0.0026. Lambda is this much. These values have been known by this formula. Phi is this much. XU by LW is 3.3138 and XU limiting by LW is this much. So hence XU by LW is less than XU limiting by LW. So beta is calculated by this formula. So this much is the beta, and finally you have to put all these values in this formula. You will calculate the mu. This is the moment capacity of shear wall. So moment capacity of shear wall is 5044 kilonewton meter, right? So we have to find how much the extra moment is getting on this wall. So extra moment is factored moment. We have already calculated factor moment is 6876 by this formula, by the earthquake, and this much is the moment capacity. This is 5044. So factor moment minus moment capacity is this much is the moment for which we have to design the boundary elements, right? So fraction of boundary element area, this is 0.125. Fraction is this area divided by the whole area. So this much is the fraction, 0.125. Total compressive load on the compression side, this much is the 3.32 is the total compressive load by this formula. So factored compressive load, so you have to multiply by this fraction on to this. So this is 0.429 kilonewton, right, on compression side. And the same for the tension side. This is the load and this is the factored. This is 0.125 multiplied by this. This is 286 on the tension side. So finally the total force on compression end is F compression. This is 429 plus M by C, that is the moment, that is the extra moment divided by the center to center distance, this much, right? So this is 952 on the compression side, total compressive load, and same for the tension side. This is 286, the factored compressive load on tension side, minus this one is minus moment divided by C, center to center distance. So 237 is the load on the compression side. This is negative. Now we have to design the boundary element as a short column. So if you provide a minimum reinforcement as 0.8 for the column, so this is the ASC required. Now the capacity of the boundary element by this formula is 1518 and the maximum load, compressive load, is 952. So 1580 capacity is more than the total compressive load, then it's okay. Now the largest dia of the bar, TW by, this is the TW is 250 divided by 10 is 25, right? Assume bar dia. So if you are assuming 16 mm, so 4.98 is required. If you choose 6 numbers of bar, so 6 number of bar 16 mm dia is to be provided in this boundary element. So AST provided is 1206. Check for the tension side. This is the load, this is the tension load. So check for the tension side. So area is required is 658. We have already provided 1206 on both side, tension and compression side. It is more than 658, so hence okay. So check is okay. Now the confining reinforcement in the boundary element. This is the boundary element and confining reinforcement, where the H is the largest dimension of the link measured from outer face, right? In this case this is BC on this side and this is HC on this side, outer to outer face. So we have to choose larger of these two. So if you are choosing a clear cover for the column as 40 mm, we know that. So HC is, this is D is 500 minus 2 into clear cover divided by 2, 210, and BC is T, this is 250 minus 2 into clear cover divided by, sorry, this is 170. So H is the largest of HC and BC, the H is finally 210, right? So rule for spacing, 1/3 into minimum dimension of BE, this is 83, minimum is this much, 250 mm. So 6 into smallest dia, we have provided 16 mm dia. This is 6 into 6 means 96, and this is 100 mm. So if you are assuming 8 mm ties, ASH SV is 79, and we have to choose the smallest of these four. So this is 79, this is 83, 96, 100 and 79. The smallest is 79. Spacing provided is less around of 70 mm. So provide 8 mm link, 70 mm center to center. So this is the elevation for the special shear work with boundary elements. You will get all the reinforcement detail. The vertical reinforcement 10 in bars at the rate 180 mm center to center. Horizontal, this green color is horizontal reinforcement in the shear wall. This is 10 mm bars at rate 250 mm center to center. This is 3000 mm for the shear wall, and this is boundary element. We have chosen 500 mm. So these are the vertical reinforcement, 6 number 16 mm dia, and these are the ties 8 mm links at 70 mm center to center. Right, if you change this one is 1%, so you need to increase the number of bars. So this much is 8 16 mm dia you have to provide. So if you change these the values, you will get the different values according to your requirement. So friends, if you like this video, if you want this Excel sheet, please contact me on my WhatsApp number and mail me on my mail ID. And thanks for watching, and please subscribe the channel for more design videos.